Now we'll look at our last lemma and theorem of section 2.4, neither of which I'm going to prove. One of them, let's see, you'll have a homework assignment similar to the proof of one of them. Let's take a look at the lemma. If we take a function f that goes from the closed interval from a to b into r, and let's call it an increasing function, and for every x in the open interval, so just leaving off the endpoints of a, b, let u of x be defined as we did just a few minutes ago. The infimum of the f of t's, the values of the functions, when t is bigger than x. And L of x is the supremum of the f of t's when t is less than x. All right, that's the setup. Now you may remember from the previous picture we had, you may be able to figure this out. The function f has a limit at x naught in the open interval a, b, if and only if. Anybody want to take a guess? It has something to do with U, capital U, and capital L. Anybody want to take a guess? Remember when I was doing this? If it goes like this, there's no limit.
They're equal?
Yeah, they have to be equal to each other. So in this case, we have to use x0. So U of x0 is equal to capital L of x0. Again, that would kind of mean that they are meeting at the same place when they get to x0. The proof is in the text, and you'll have a homework problem, which is going to be essentially writing that proof out, but you'll do it for a decreasing function. Okay, so the statement is the same, whether this is increasing or decreasing. But the proof, you'll have to just tweak a few things so you can get that out of the textbook. All right, lastly, theorem 2.8. The function f, just like in the previous lemma, going from closed interval a, b into the reals, let it be a monotone function. And if you take some subset of the domain, being defined as the set of points at which f does not have a limit. Okay, so the set of points x naught, say, where u of x does not equal, u of x naught does not equal L of x naught, that's going to be a countable number of points. So that set D is countable. I remember really diving into that in a class that you would take beyond real analysis called measure theory. And finally, if f has a limit at x naught in a and b, then that limit happens to be, as x is going to x naught, f of x naught. That would be the u of x and the L of x. I'm sorry, this would be u of x naught and L of x naught.